Welcome to part 2 of the Adapt Builder training for two-way post-tensioned floor design in Adapt Builder. This is a continuation of a webinar that was presented a couple of weeks ago, and today we're going to focus mainly on, we're going to summarize and go back a little bit in terms of the tendon optimizer. Look at the model that we had originally started from. There were a few issues that we've had to resolve between now and when we conducted that first webinar. We'll talk a little bit about punching shear and then production of the strength reinforcement. So to summarize, we had a model, and in the model what we were finding were just a few issues with some of the results for bending moment, which trickled down into the stress results and so on. And there were a few things that we've done in this model to clean that up. Now the main reason that that model was having a few issues was if we go to a side view, we can see that the way that the columns and walls are connected to the slab. And here we can see that the columns are connected with an offset. They're actually modeled to the reference plane level 6, and then they would have an offset equal to the slab depth. We had changed the slab depth from 9 inches to 8 inches. So these columns on the bottom originally had an offset of 9 inches. There was actually a gap between the columns and the slabs, and that was causing essentially the slab to really cantilever off of this core. So we were getting negative bending throughout, most of this inner region of the slab in the model. It was essentially cantilevering off all 4 sides in that model. So we went back and corrected that. That was an easy correction. We just went to Model, Connect Supports, and that's a good lesson. If you ever modify the slab thickness and the columns have an offset already assigned to them, that offset doesn't change until we either manually go back and modify the offsets for the columns, or we can use this pre-processing option here to connect those supports. So that's what we did. We selected that. We then also we made a few adjustments to the support lines in the model. So in this direction, in the Y direction, actually in both directions, what we did was we went and we modified the minimum number of sections from 3 to 2. And that cleans up the densification of the design cuts at these walls a little bit. It produces less design cuts per span, or if the point is located in the wall, less design sections within the wall. We also adjusted the way our splitters look. So if I go to floor design and I turn on the splitters, we have a few splitters here bounding the outsides of this opening so nothing crosses into the opening. You'll notice I actually removed that wall, that inner wall, and just stretched out the opening. That was also something that I did to just clean up this model in terms of the meshing in the model. That inner wall that wasn't absolutely necessary in a single level floor, so we created that or modified that particular region of the floor. In the other direction, in the X direction, we added a couple of strips here and over here just to refine the design cuts. Okay, earlier the cuts were being integrated really from here all the way down to here and then like so. So we just brought in this cut and this cut just to break that up slightly. This is a uniform direction, so we still have uniform cables through this region here. We have banded cables. Let me color that in blue on the outside, so these bands pick up the uniform cables in the X direction for those new strips that were added. So in terms of the splitters in this direction, if I turn on those splitters, we just have a couple of splitters again to bound the tributary from entering the opening in the middle of the slab here. One thing you can do if you wanted to go to reports, we can go to design strips and we can look at the design strips in the X or Y. This really gives us a hatched view of the different tributaries that we're working with that we've actually created. You can see a few little things here. Because this support line, the point actually stops at the middle of the column, and this one extends out to the slab, you get this section which goes from this point up to this point. Had this support line been extended out, this would have been just a cleaner line along there. But ultimately, these tributaries are used to produce design cuts. Those are what are being evaluated for the design of the slab. So you get a small change here in the width. Like if you look at this one right here, there's a change between this cut and the one to the right in terms of its length. If you wanted to clean that up, you could go back and adjust this point. I can move that out, or I could actually put a splitter along there. That's a pretty minor difference between the two. So we're going to just go ahead and leave that alone. We'll kind of reset from where we ended up with during our last training. I'm going to analyze the entire slab again. We're only looking at gravity combinations, surface and strength. We'll continue using those same combinations that we had run previously. Okay, and once that's done, I'm going to go ahead and from floor design, we're going to design the sections again. Where we ended up last time, we talked about meeting the serviceability requirements of the slab, and that's necessary in order to determine what post-tensioning we need, what forces, what effective forces we have in our strands, what the position of the strands are with respect to not only the depth of the slab but also in plane. All of those affect the strength calculations in the program. So before we go into determining what the reinforcement requirements are for not only service minimum reinforcement but strength, we have to get a good feel, and we have to kind of hone in on what the post-tensioning is going to be in the slab. And that's all judged and designed, we'll call it, through requirements that are given in whatever design code you're working in. Some design codes are a little more lenient with the ability to exceed an allowable stress, but then add reinforcement for crack control. And then there are other codes where you have to meet hard limits for allowable stress. So if we look at, let me go ahead and collapse that. I'll come back to design sections, actions, or excuse me, stresses. Bottom stress, for example, we have a few regions here where our stresses exceed allowable. The allowable stresses are set under the criteria, and this is set to 6 square root of F prime C for a two-way slab. We have other settings for one-way slabs and beams, but you can see this is exceeding that allowable value. So this is an area where we may have to add, this is a uniform cable, we might have to add tendons here, pull those out in this direction in order to take care of that stress for that one region. In other regions, and here I'm just assuming that the pre-compression is working. If I go over to the Y direction, we have several regions here that don't work. So again, this may be a case because everything's kind of happening down here on the bottom end. I would want to switch over and look at my top stress. You can see there's an exceedance here, there, and then here at the core wall where the tendons are kind of coming off of that corner, we have high negative moment. So in this case, we may want to add tendons here that are anchored back behind this wall, maybe even here also. In this case, we have issues with overstress at supports on the two interior supports. So here, and then we have issues down here for bottom stress. Here we may actually just increase the number of bands through all three spans. So you want to make sure you look at both conditions and determine what might be the best solution for that condition. And what we're going to do now is let's go over and peek at pre-compression. So pre-compression, we have a little bit of a drop. I think we had discussed pre-compression during the first meeting. We would need to go through and make sure that these are satisfied in terms of the minimum requirement. Here we're working really with 125 psi for minimum pre-compression. I'm not going to go in and modify these. We're just going to assume that the pre-compression here is fine. But we certainly want to make sure that we check this and that the pre-compressive levels in the slab meet the minimum requirement, and also we don't want them to exceed some allowable value set in the program. In our program today, in this model, we're using a maximum of 300 psi. Now we don't graphically code check 300, but again, the user would want to make sure you look at the maximum value. I mean, here the maximum really the maximum compression is 677. We reported as minimum there. And we may want to know exactly where that is, because that's a pretty high value for pre-compression. So we would need to go and determine where that occurs. Well, if you see right here, there's a big spike right there. And that spike, see if we can find that. Yeah, that spike is this section cut right down here. So this section cut is shorter than, let's say, the other cuts. It's kind of encroaching on the slab edge there, and everything is starting to come down to a point. And then we have tendons. Okay, so that we have tendons that come through here. Let me turn the tendons on. And we have a lot of tendons kind of passing through this joint. So this is really a function of how the strips are set up and how many tendons are kind of converging in this area. And if we look at this cut, we have 2 sets of tendons times 9 times 2. So there's 18 strands intersecting that cut. Now if we go to the P over A check, that could smooth that out a little bit, or it could increase like it has here. Now we actually have more force, because now some of these tendons over to the left are contributing to the in-plane precompressive stress in that area, and we're really just integrating over that stress here to get this value. So something would have to happen here. This is probably too many tendons that are converging on that one column in this model, and you get that high spike in precompression, or the user just has to make some judgment as to whether that is a acceptable level of precompression in that zone of the slab. So let's go back. Let me turn the tendons off. I'm going to go back over here to stress. Now before we move into looking at punching shear and strength level design, punching shear, similar to flexural design at strength level, really could be affected by the post-tensioning. So we want to, again, make sure that we solve our issues related to serviceability of the post-tensioning before we go into those designs. You certainly can go ahead and run those designs and see kind of ballpark where you're at with the level of reinforcement and the punching shear, but for a final look at that, you want to make sure that the tendons are where you want them to be. So we're going to talk a little bit about the tendon optimizer. I'm going to go back and I'm going to run this in a couple of different spots. And we did this in the first webinar on a sample model. We're going to now apply it to this real model that we had been working on, that we had started. So let's go over to the X direction. We have uniform cables in this direction, and we're really concerned about this, let's say this span right here. We have an overstressed condition. The allowable for this span, if we look at the criteria, the slab is 5,000. So the allowable is 424 psi. We're up at 540. So we're right around 20% overstressed in this zone. This is a two-way slab. We're going to go ahead and try to optimize it for just the service total condition. And what we'll do is we'll go over here to tendon optimizer again, and we're going to go into settings. We're going to make sure we set these values up based on our design parameters. So we're going to leave these really as they are. Everything here is set kind of to what we want to begin with. So we'll leave these as they are. It's important that the user kind of understands the inputs here, what load balancing we want to use, self-weight plus dead load. How do we want to report the stress, ratio, factored, or the actual value, precompressive and load balancing ranges that we're working with. So all of these settings affect how the program targets this one area and comes up with an optimization or a design to solve this span. And so once we have set up our settings, let's go back, and I'm going to select the tendons that I want to optimize. I'm really selecting the tendons that are contributing mostly to this span. I mean, there's some contribution from these adjacent tendons, but these are the primary tendons, let's call them, for this span. And one thing you'll note here is if you go back to settings, you can see this 5% is way too high. So this first cut A right there, let me do that in black. That is actually this distance away from the column face, and we want the program to have this cut somewhere out here and over on the C side somewhere, you know, like so. So we might want to adjust that. If we let me adjust that to 1% and update. That's pushing it further now to the left, but we can still see it's pretty far away from that support. And what's likely happening is it may be being referenced off of that corner of the slab. So that's something that we'll have to check. I mean, obviously there's not an overstress here, so it's not as critical here, but you want this cut to be as close to that face as possible so that you can compare it with the cut and the values that are calculated per the finite element results versus this optimization result from this actual algorithm. And so let's go ahead and take a look at some of the values. We have 3 strands that are being categorized for this strip. The current total force is 320. The estimated force is actually 544. And you can see the precompression right now in this strip is about 281. So that's already really high for this span. If I increase our force to 545, our precompressions are at almost 500. And the load balancing is at over almost 150. But that may be necessary in order to meet the stresses that are controlling this zone. So we could go and just use this as a guide to determine whether or not this is actually going to work. In this case, I probably would not apply that force because of the precompression level and the load balancing level, and we may have to come up with another solution that is feasible for this portion of slab. Maybe that includes a thickening of the slab regionally. It might include addition of another support, movement of a support. But if we go ahead and exit out of here, and I'm going to turn back on my P over A, you can see the P over A in that zone is already pretty high. It's 270 here on the end, 280, and then it dips down to 250. So adding the necessary number of tendons in that zone to meet the allowable stress may bump that precompression up way too high. So that's one way to use the optimizer. I'm not going to apply the predicted value or the proposed value to that region. I just want to see what it's proposing. That tells me I may have to do something different in that zone. If I switch over to the to this direction, let's go back and let's look at the bottom stress. And I'm going to take one of these as an example. This stress is also really high, but we may also have less precompression, so we have more room maybe to add more post-tensioning in that area. So we could go through the same type of exercise where if we go back to our tendon optimizer, okay, and I need to kind of know what the tributary width is on average for this strip. So I'll just use this section. Let me just exit there for a sec, and I'll go to the design section. This is roughly 243 inches for this strip, and that equates to about 20 to 21 feet. So let's go and come back into optimizer. We're going to go to settings. This stuff is going to be changed. Remember, all of these settings need to be adjusted as needed for the design, and I'll just select those 2 cables that we want to optimize. You'll notice the program proposes a tributary based on the position of those cables. We're actually going to go back and modify that. We're going to say 21 feet for the optimization. I'm going to update that. Okay, and you can see there's some section cut here that is pulling that point of the strip. Okay, let me change the percentage here to 2. You can see that's kind of pulling down now. Let's go to 5. And you can see it's all based on that point and something out here. So let me let's exit out of there just for a second. What I'm going to do here is actually disassociate, turn the tendons off. I'm going to delete this point right there, and then I'm going to come back and just isolate this one strip. So I'll create another strip, but it's not continuous with the other two spans, and then we'll go back and generate the design cuts. I'll just design the sections again just to get an updated result for the strip design. And we can see if we go back to bottom stress, we still have that same issue. And let's go back into Tendon, see if that helped us with this problem. So under Tendon Optimizer, we'll go back, select these two cables here. Let's change that to 21. And it's still pulling that area. So we're going to just ignore that for now. Let's come back into Optimizer. You can see the current force is 374. We have a bottom stress here that was overstressed by about by about 77%. If we increase the force from this to this, we get that down to about 1.1. So the pre-compression is a little high if we do that. It's not exceedingly high like the previous example that we gave, but it's you know 15. It'll likely end up 15 to 50% over 300, or 15 to 50 psi over 300. And then the load balancing is we have plenty of room there. So this is a case where we may want to apply this change to the model. When I go to apply this, it could be done as a distribution between the two cables, a single modification to one of the current cables, or a new tendon. I could add a tendon from this point down in this zone. And if we add this, this is design cut C here, so I'll say add from C, apply. The program actually adds that add tendon right there with the total delta. There's my add tendon, and this is the shape of the add tendon. This is the tail in this area right here. This is essentially 9.83 strands. So we may want to round that up, but that's how the program would essentially apply an add tendon in this type of a condition. Okay, so let's talk now about, we're going to just again assume that our tendons have been worked out, solved. Once we do that, there's really two main areas of strength that we want to consider, and that might be punching shear, two-way shear at the columns, and also the flexural reinforcement in the slab. So we're going to first look at the punching shear. After we've analyzed, if we've updated the tendons, we want to make sure we go back and we reanalyze, if we haven't yet, for those new forces in the cables, the new number of strands, the new position of the cables, vertically or in plane. And we're just going to come back and say, okay, execute the analysis again for our combinations. This updates the solution based on the current set of components, the placement of tendons. And after that, we'll go to floor design, and we're going to go to shear check. We have a few settings here for shear check. I'll hit on a few of these, but what I recommend the user does is go into the help file. Let me come out of here. Under documentation, there's a new features supplement. This new features supplement gives description of all new features that were included in version 2019. If we run down here to punching shear, section 2.6, that just gives you nice, concise summary of what we've modified for punching shear, specific here to ACI 318 in this version of the program. So coming back over to the settings, if we select stud, we have two options, stud or stirrup. Let's assume we're using a stud. I'm going to change the diameter to 3/4 of an inch, and the number of rails per side is set to 2. Now this input could be overwritten, or overruled rather, by this option, limit rails to 2 times the effective depth. So if we have a square column that's small, maybe it's 12-inch, 2 rails may work. Right, this may satisfy code. There's a code requirement that this spacing here be less than 2 times effective depth. So if this column grows, then we actually may need 3 rails. Okay, the user would have to manually determine what the minimum number of rails is and enter that here, if this option is not selected. If this option is selected, that program will do that automatically. And this is more helpful, especially with like rectangular columns where we might have the need of 5 rails and maybe 3 rails. If this is set to 2, we don't want just 2 and 2, we want 5 and 3 because that satisfies this code requirement. So this automatically fills in the number of rails needed on the side of the column. There's also this option here for, so we're going to leave that to 2, I'll select that. We have the ability to either check the stresses for each moment separate. So if we look at the local axis orientation of the column, we have R and we have S. This is 0-degree rotation, and so if we have bending, this way and maybe bending this way, we have the vertical shear produced from the axial force, or let's say the load coming into that column vertically, and then we also have our stress due to the bending. So that stress can either be combined or it can be checked separate in both directions, and that's what this setting is for here. The columns can be categorized as interior, which would be a 4-sided critical section, exterior or end, which would be 3-sided, or interior, or excuse me, corner, which would be 2-sided. So if we have, and I don't know that we have this condition at all in the model, it doesn't look like we do, so I'll describe it through some illustration here. If we have a free edge of a slab, and let's say we have a column, this column would be categorized as exterior and edge. So bending about one direction, we're bending, maybe parallel to this free edge. Bending the other direction, we're bending normal or perpendicular to the free edge, and that changes the way we calculate the centroid of the critical section and consider the stresses based on the angle or the direction of bending. But this ultimately is a 3-sided critical section. The critical section here, by assumption and by default for the program checks this dimension from the face to the edge of column. If this is less than 4 times the slab thickness, I'll call that H, the program just assumes that there's a free edge on the back side of that column. It ignores this back here. And so that free edge is then created, or the design cuts are created based on this virtual free edge of the column. So it's somewhat conservative. If you want the extension to the actual physical location of the slab edge included in the design cut, then you actually could include this, extend critical section to slab edge. This would apply for end edge or for corner. So a corner condition might look like this. If we have our corner here, the column is inboard. Both this dimension and this dimension both fail the 4 times H test. The program by default would assume that this is the free edge here, and the critical section is here. If you want that to extend out like so, then we use this option right there. Okay, the next option is provide uniform spacing of studs. The program simply takes the total required number of studs, and it would then take the minimum spacing for those studs, divide that by the total length of the rail to get the uniform spacing. This becomes conservative because the way that the program checks the column is, if I have multiple, this might be what we call layer 1, it's critical section 1, then we have layer 2, and this just works its way out from the column until there's no reinforcement required. Well, the reinforcement between this zone, I'm going to call this A, and this zone we'll call this B, and this zone we'll call that C. The per calculation reinforcement for A, B, C, D, etc., those could all work out to be unique, meaning the spacing is different for each zone. You might need 2 studs at 3 inches here, maybe 4 studs at 1 inch here, 5 studs at 1 inch. So each one of these zones could technically have its own spacing and number of studs. Just this is based on, again, the calculation of required shear reinforcement within that layer. and that also is subject to minimum reinforcement requirements that are needed between each critical section. And so the program, if you have an output that says you need 3 at 2, let's say 2 at 4, and then 5 at 1, if that total rail length equals 20 inches, the program, when it applies uniform spacing, is going to say take the 1 inch, calculate the number of studs needed to satisfy 1 inch spacing at 20 inch length. So now I might need, instead of 3, 2, and 5, which is 10 strands or 10 tendons, I might need 16 tendons. Actually, this would be maybe 19 studs, 19 at 1 to get the 20 inch length. So this will normally end up in having more studs in order to meet the uniform spacing, the way we handle that, versus just the direct outcome of the solution, where you could technically have different levels and increments of spacing. Okay, that's what that option is. I'll leave that turned on. Consider critical sections outside of the shear reinforced zone. This just means the program is going to come back and we're going to check if you have a column here, and let's say normally our critical sections are rectilinear. Now wherever our last critical section that does not require reinforcement is checked, the program would come back and check that same critical section for this shape, kind of this octagonal shape. If the stress exceeds 2 square root of f prime c for that critical section, then the program just continues to formulate those until we fall under 2 square root of f prime c. So this satisfies the requirement to check that octagonally shaped critical section. It's really a function of the reinforcement layout. It's really the least critical section, and our assumption here is that the rails project perpendicular from the column. So the least critical section is this, is this shape. If you had a column that had, rails off the corners and maybe even off the sides, that least critical section now, might look like this, like a square. So, but the rails would be longer technically. So our assumption is kind of this top image. That's how we're laying out the rails, and this is the least critical section for that configuration. And then the last option here would be in high seismic zones, where we may have to meet requirements, minimum stress of 3.5 square root of f prime c within 4 times the slab thickness. If you need that requirement to be met, then you would just select this option. The program would make sure that there's enough reinforcement to meet that requirement per code. So once we set up our settings, then we're going to go and we're going to just execute punching shear, and that's completed. Now there's graphical code checks, and there's also tabular results, and also Excel data that you can get more information as to the results of each of the different columns. First thing we'll check is over here in the result display settings. I'm going to go to envelope of strength. We only check punching for strength combinations, and those are designated under load combos here for strength. Okay, we'll go back under punching shear. You can see the status essentially. So we have several that are reinforced. We actually have a couple here that are not being checked, and here I would have to actually move this slab edge out so it covers those columns for those to be checked. I just didn't make that modification. This one checks because it's outside or on the face of that outside column, that corner column. But we have just a brief status check. If you want the colors to be a little more vibrant, I could always turn off the upper columns. I'll just hide those, and now you can see the colors kind of match what's shown here. That gray column above mutes the color somewhat. So there's several that need to be reinforced. I can look at stress ratios, the condition. These are the conditions that are being checked: corner, edge, and or interior. And then also there's a shorthand abbreviated kind of reinforcement shown on graphically. So If I go to here to the font height, let me just produce a larger font height. Okay, and if we take a look at this interior column, this means we have 14 total rails. So there are, and we have a legend up here you can follow. There are 3 rails, okay, 3 rails along the R direction. So the R direction is this way. So there's 3 rails, 1, 2, 3, 1, 2, 3. This is an interior condition. That means every side achieves a rail. In the other direction, in the S direction, which is maybe this way, we have 4 rails. So 1, 2, 3, 4 on both sides. So there's 14 rails. And on each rail, we're going to have 13 studs at 3 inches on center with a total rail length of 39 inches. That's how this can be interpreted. If you want to get a kind of a schedule format of the reinforcement, we can go to reports, punching shear, and we can look at the punching shear reinforcement. This just shows each of the columns with their number of rails per side, total rails, and just other information for the stud design. If you want more detailed information in terms of the calculations that follow our implementation, we could go to the option here for punching shear report. This is an Excel file. So if we open up that file, there's a lot of data in this file for critical section geometry at every column, stress checks, required steel reinforcement, and then this is just a reflection of that schedule that was just shown. So this can be used in conjunction with our implementation documentation for punching shear. We have that for many different codes, design codes, and then these numbers could be verified using that technical literature. So that is how we would check punching shear and output that information in the program. We're now going to go ahead and look at Flexural results. Now for minimum reinforcement for a two-way slab, we can always produce minimum reinforcement separate from strength reinforcement. And remember, we've already designed our section, so all of this information is there in the background. If we go to floor design and I go to the option for calculate rebar plan, okay, let me go back and just redesign the sections. This will become active. I'll calculate the rebar plan, and you can see that there's options to envelope reinforcement for all load combinations. I can envelope only for service, for strength, and so on. The settings for reinforcement, if we go over to the rebar tab, there's options for rebar cover. I'm just kind of using the defaults here for when we started this in part 1. Rebar size and material for two-way slabs. Here I'll set this to number 5s, top and bottom. I could set up some rebar roundup spacing type of settings if I want to round my bars up or round them down in terms of the spacing or the actual bar length. I can use some of those settings. How are the bars going to be calculated in terms of their length? Well, minimum reinforcement has cutoff lengths over supports, cutoff lengths referenced from the middle of the span, and then we have bar extensions as well, and whether or not we want to adjust the lengths to center bars in the span over support. So there's a few options here to customize the way the reinforcement's being handled automatically when we generate that reinforcement. But ultimately, we would need to go in and calculate rebar. And if I calculate this for service, and I go ahead and execute that, this is the rebar that's needed to meet minimum requirements per code. So you can see all the rebar aligns with the support lines. It's parallel to the support lines. If I come back and generate that rebar through use of the same dialog, however, in this case, I'm going to align it relative to these axes. Now you can see everything's aligned, and we do a conversion for the quantity of reinforcement in the slab. Top reinforcement is green, bottom reinforcement is red, and you can go in and customize the display of the rebar using these display manager options here. The user can make customizations to any reinforcement on screen. If you double click this, I can change the size, number of bars, length of bar, whether it's distributed or grouped, and so on. So there's different things you can do to individual bars or groups. If I select this and this, and I have two bars selected and go to modify that selection, there are some modification options under rebar right here that you can apply to a group of selected bars versus individually. Okay, so this is the output for the minimum requirements for that slab, and all of these bars correlate back to a design strip. They're all based on a strip. For example, this 12 number 5s here at the bottom, if we go back and look at the Y direction strips and I look at the stress for, let's say, envelope of service, the bottom stress, the maximum is around 295. So anything over 2 square root of F prime C requires reinforcement. That's where that reinforcement comes from. It's based on this stress that's essentially calculated based off the integrated moment and the precompression in that one section. So this is an output of the minimum reinforcement. If we go back and we look at the strength reinforcement, I'll go back and just envelope strength instead of service. This now is the output of the strength reinforcement. And you can see there may be more bars for strength at the same position that there might be for service. Back to that example, for strength at this location, I need 6 number 5 bars. The tendons contribute quite a bit to the capacity of those sections. And if I go back and toggle that to service, envelope service, I need 12 number 5 bars. So service would control in that region. If I go ahead and just envelope everything, we're going to see 12 number 5 bars. That controls that location. So the user can play with the way that the bars are represented graphically in the model. And one thing we can do to help us kind of understand what's controlling in a certain region, let me go ahead and turn off the rebar. I can do this either by going back to my default display, or I can go to rebar, turn the rebar off, show or display rebar. Let's turn back on our design cuts. And I'll go to this Y direction. If we go to investigation, I can see moment capacities with demands. And I can also see demand capacity. Now these numbers, we're getting some strange numbers again here. You can see this section. Let's see. Yeah, that section right there. If you look at the design cut, if I actually double click on that design cut, and you can see that the design cut's actually using the wall. It's referencing the wall as part of its section, so you get really high effective depth. If you go to details of the reinforcement, you can see kind of the reinforcement details, CG from top or bottom of section, but I can tell that this is just an inaccurate design cut because this value does not show the actual physical representation of the cut. If we go to this one, for example, let's do that one. You can see this shows me the actual physical dimension. This shows me the idealized section cut, and we have some real numbers here. So this is skewing the results again, just that cut right there, and it looks like another cut over here somewhere. But this investigation tool allows you to see demand with capacity, and a lot of times you can determine quickly where minimum reinforcement controls, because you typically have some reserve capacity between the two graphs when we look at that result. So let's try this. I'm going to get rid of these two strips to see if we can get results that we want to show here. Let's go back and regenerate and design. Oops, let me add some splitters there. Okay, because I removed those, these are now stretching over to just the created tributary boundary kind of towards that inner wall. But what I can do is add a splitter to, I'll just take one from here and just up like so, and then here I'll just kind of follow So we'll regenerate that. We're ignoring that middle section because of that problem where we're having that high capacity being reported. Okay, and then once I have done that, I'm going to come back and check moment capacity with demand. So this is the graph that we wanted to look at, and I'll go to that region here up top. Let me change the font size. I'll scale that back down. The green is the positive capacity, blue is negative capacity, the gray or the dark color there is the demand. That's the envelope of demand at strength level. So where we have a gap between here and here, we can usually tell that's a region where minimum reinforcement controls. Where we have this stacked and the demand capacity ratio is 1, that's where strength would control, because the program is having to add enough rebar to meet the demand, and usually the demand graph and the capacity graph are stacked on top of one another. And the user can always double click on any design cut and see some of those results. You can see here service total controls the amount of bottom reinforcement at that cut, whereas over here if I double click on this cut, strength controls the demand at that cut. And so the user can just go through and review those results graphically in either direction using these settings under the result display settings. The last thing we'll show in terms of reinforcement for strength is the ability to actually check the area of steel along the design cut. Let me turn off my splitters, and I'll expand this reinforcement. For the required calculated reinforcement, let me go back here to envelope of everything. We can go to calculated required. So this shows me the top reinforcement and bottom. Top is green, bottom is blue, and shows me the area of steel required at those design cuts. This is maximum steel or enveloped steel for the strip. You can also see provided. Provided requires that we actually generate the rebar for the selected combination. So for envelope, I'll create that, and then I'll come back and just toggle back to provided. So this is what's provided for those different locations, the area of steel that the program has added to the slab. And then you can look at base reinforcement, area of steel, or percentage relative to the section area row. This is the reinforcement ratio in the section. Those are a few ways to graphically check reinforcement in the slab. We'll go ahead and conclude there. If there are any questions or concerns about the content in the webinar, please feel free to contact us at support@adaptsoft.com, and we'd be happy to give you assistance with any questions you have. Thank you.